Welcome back to day 2 of differential equations. We just got done talking about slope fields and direction fields and autonomous differential equations, what that meant for our slope fields or direction fields, and classifying the critical points of a differential equation. So now, sort of continuing our tour of topics from calculus, let's remind ourselves of a specific type of differential equation, a first order differential equation, which can be written or is of the form dy dx is equal to some function of x times some function of y. Perhaps we don't use f here because f in this context already has a different meaning, the right-hand side entirely. So if a first order differential equation of this form, where dy dx is equal to g of x times h of y, is said to be separable. And the direct consequence of that, what that means to us, is this differential equation can probably be solved using integral calculus, using just the techniques of integration we already know. So let's look at a couple. If I tell you that dy dx is equal to x, we saw the slope field corresponding to this in a previous lecture. If I give you this as a differential equation, we can solve it. This is, again, saying dy dx is equal to x. So we can integrate both sides with respect to x. The antiderivative of the derivative of y with respect to x is y. As a function of x, the antiderivative of x is 1/2 x squared plus our constant of integration. Remember, this constant of integration pops out because our original function could have been any function 1/2 x squared plus a constant, because the derivative with respect to x of that constant is 0. What we have here is the general solution to the differential equation. It is also sometimes called the family of solutions to the differential equation. Let's say I have that y dot, the derivative of y with respect to x, is equal to y. This is also separable. This is using some technology, or using some terminology from last lecture. This is an autonomous differential equation, but that's actually not important necessarily to note in classifying separability. I can separate this because it is 1 over y dy dx, and that is now equal to 1. I can divide both sides by y. Doing so gives me 1 on the right-hand side. And now I can integrate this with respect to x. 1 over y times the derivative of y is exactly the derivative with respect to x of the natural log of the absolute value of y. Antiderivative of 1 is a constant. A constant times, that is false. The antiderivative of 1 is 1x plus a constant, because the derivative of x is 1 and the derivative of constant is 0. We are generally loath to leave solutions like this. We like solving things for y. And if I solve this for y, I get y of x is equal to some new constant times e to the x if I retcon this as c1. Now, when I take e to both sides, I get e to the x times e to the c1. E to the c1 is just a new constant. And by allowing y could be negative here, by allowing this constant the freedom to be negative, we take care of all possible solutions. Again, this is a general solution, also called the family of solutions. But you'll notice we haven't done anything new here. This is still just calculus, even just integral calculus with that. Even y dot is equal to y squared x times e to the 3x plus 4y. Now, I probably don't feel compelled to do this for the fun of it, but this is still separable because I can write this as 1 over y squared e to the 4y dy dx, and that's equal to x e to the 3x. Double checking, this breaks into e to the 3x times e to the 4y. I can divide both sides by e to the 4y. I can divide both sides by y squared. That leaves me with an x and an e to the 3x hanging out on the right-hand side. And so I can integrate both sides with respect to x. And maybe I remember how to, maybe I know how to do this, maybe I don't. But I was still able to separate it. And so it's still classified as a separable differential equation. If you have a separable differential equation, your ability to solve that differential equation using techniques that you already have is based on whether or not it can be solved using techniques you already have. But it is separable. Now, we do have to be careful here, right? Because I've been manipulating these equations algebraically, and anytime we manipulate equations with variables algebraically, we should understand that there are certain rules we have to abide by. For instance, we can't divide by 0. Here, I didn't divide by anything. We're good here. This is good for all real numbers. Here, I divided both sides by y. So this solution only works provided that y itself is not 0. And here, this solution only works again, provided that y itself is not 0. And so truly, each time we divided by y here, we split into two universes. In one universe, y is 0. And if y is 0, then the derivative of 0 is 0. That's also a solution to this differential equation. So either y equals 0 or y equals some constant times e to the x. You could choose 0 to be that constant. So we're actually okay. These parallel realities converge to a single solution. In this case, it's possible that y is 0. That would be one solution. Y is 0. If I plug in 0 here, I get a true statement. So y equals 0 is a solution. If y is not 0, then I have to solve this. But we do have to be careful when dividing by variables. So let's look at the differential equation 1 plus x dy minus y dx equals 0. This is a differential equation in the truest form of the phrase because it is an equation involving differentials, not just like the derivative of y with respect to x. This is separable because I could rewrite this as 1 plus x dy is equal to y dx, and then 1 over y dy is equal to 1 over 1 plus x dx. Now I can integrate both sides here to get the natural log of the absolute value of y is equal to the natural log of 1 plus x plus c, which gives me that y is equal to, retconning that to be c1, some constant times 1 plus x. Now, in both, there are two different cases here. In one case, y is 0. In the other case, x is -1. I have to abide by both of those requirements. If y is 0, well, that could just be a c is equal to 0, so that's encompassed in the solution. X is -1. Well, that gives me y is equal to 0, so that's actually a consequence. Or y equals 0 is a consequence of this being the case. But we have to acknowledge that at least. Okay, so sometimes we can find general solutions to the differential equation using techniques from integral calculus. And sometimes perhaps our techniques from integral calculus fail us. So let's continue down this rabbit hole of integral calculus. Say I tell you dy dx is equal to -x/y. And I want you to solve this differential equation subject to the constraint that y of 4 is equal to -3. We should feel very comfortable with this problem, because this is exactly the type of problem that we've been asked before. This is separable, so I'm going to isolate my variables. And then I'm going to integrate both sides with respect to x, which gives me that the antiderivative of y is 1/2 y squared. Antiderivative of -x is -1/2 x squared. And then I have my constant of integration. What I have here is the general solution to the differential equation. I can clean this up a little bit if I want to, if I feel so inclined. For instance, I can multiply everything by 2 and get y squared is equal to -x squared plus some slightly modified constant. I could even say move the x squared over. I get x squared plus y squared is equal to c2. All of these are different forms of the general solution because they all exhibit the same relationship between x and y. Now let's apply our condition. Our condition was that y of 4 is equal to -3. So that means when I plug in 4 for x, I better get a -3 for y, and that needs to be a true statement. So I need to choose C2 so that this is a true statement. C2 in this case is equal to 5. And so this gives us the particular solution, x squared plus y squared is equal to 5. It turns out 4 squared is 16. -3 quantity squared is 9. 16 and 9 actually make 25. I was skipping ahead to it's equal to 5 squared because this is the equation of a circle with radius 5. This is called the particular solution. It is the solution to a differential equation which meets the condition. It has to fit through this point. So say we have y dot plus 2y squared times x equals 0. And we're going to find the general solution to this differential equation. The first question we probably want to answer is it separable? Because as of right now, the only thing we know how to solve is a separable differential equation. Let's manipulate this by moving the second term to the right-hand side. Now I can divide both sides by y squared. I get 1 over y squared dy dx is equal to to x. Now I can integrate this with respect to x and get, well, the antiderivative of 1 over y squared is negative y to the negative 1. Antiderivative of 2x is x squared plus my constant of integration. Let's clean this up a little bit. This is y to the negative 1 is equal to c minus x squared. How about c plus x squared? And so y then is 1 over x squared plus a constant. And so we have the general solution to this differential equation. We have the general solution to this first order, nonlinear, homogeneous. Oh, we don't know that yet. First order, nonlinear differential equation. All right, I'll give you a couple examples now to attempt to separate. And if you can separate them, then integrate them. Try y dot equals xy plus 3x minus y minus 3 over xy minus 2x plus 4y minus 8. And try xy dot is equal to y squared minus y. I want you to find 3 particular solutions to this. Find the particular solution subject to the point 0, 1, and then try 0, 0, and then try 2, 1/4. So give those a shot, and then I will see you on the next video.